Welcome back. I guess today we will uh, continue uh, computing the monodromy representation. So, yeah, that's what we're going to do. Computing the monodromy representation. As soon as we got the caffeine flowing and the chat set up. Yeah, that's what we're going to do. I don't think we'll go to Reddit, but I'll just keep it open there anyways. Okay. So, hello, Edit Smith. So, actually, I want to pick different open sets than the ones I said, because I want a loop at 1. So, I think the open sets I'll take are this one. So, everything except for the dotted line. This is U. And then V will be everything except for the other dotted line. And we want to see in order to see what how a representation acts. Oh, that's cool. I like that it made a circle for me. But now how do I move it? I'll just call this one. All right. I want to see how gamma m how this loop acts, or in fact, it's enough because this is just it's the integers. I can see what what 1 does because it's a generator, and I can completely determine the associated representation. And so remember that our local system. Oh, I don't have my mic set up. I wonder if it will automatically switch over to the mic. Let's see. Maybe that worked. Yeah, I don't know. Let's see. Yeah, I think that worked. Okay, so remember our local system on really any open set. Well, for any open set, we said it was going to be solutions to this equation. And nice. Okay, it switched. Nice. So we said it was going to look like solutions to this equation. And really, this basically just looks like I guess x. I should be consistent with my variables. This really just looks like x to the 1/2, all scalar multiples of x to the 1/2. Of course, the question is, well, what do we mean by x to the 1/2, right? Square roots become complicated in the complex numbers. Well, I picked the u that I did because I'll specifically choose the branch so that in u, so over u, this will be maybe like square root 1 or something, where square root 1 of I should have done z because that's a complex variable. Oh well. Whatever. It'll be the absolute value times e to the sorry, it's the square root of the absolute value times e to the I theta over 2, where we've specifically chosen to write theta as being from 0 to pi over 2 and from pi over 2 up to 2 pi. Meanwhile, in the other coordinate, or for v, square root 2, that's a bad notation. It makes it look like whatever. It's a notation we're sticking with. Square root 2 will be, the ordinary square root of the absolute value of x. No. Also, by the way, I should have also said we're in the non-zero complex numbers. That's important here. So 0 is not included. That's our total space. No, the sheaf is defined on all opens. The sheaf is defined on all opens, but we're trying to play this game that I talked about yesterday. So we want to. So I claim that there's an equivalence of categories between local systems and representations of the fundamental group. And how do we go about doing that? Well, it's this picture I drew yesterday where basically you take a loop, as I drew here in red, and then you find some finite open cover of that loop. And then you basically take this chain of isomorphisms between the stalks and the sections over the open sets. Yeah. So we're going to compute for our sheaf that we had last time, so-called square root sheaf, because these are square roots of functions. Is this my university office hours or just general forum? Yeah, these are not my university office hours. Although I have thought about maybe I haven't told my current discrete math students about this channel, but I was thinking of possibly letting them know. And we're making some extra content for them, but we'll see. But yeah, people can you can ask about anything in these office hours. That's the idea. Anything at all. Yeah. In the second case, so I should say in both cases, I'm writing like x is e to the I theta. But I'm choosing to write it in such a way, in these two ways. I could have replaced these with the root of r. But in the second case, theta will be from 0 all the way up to 3 pi over 2, and then 3 pi over 2 to 2 pi. What's my view on mathematics Olympiads in high school? Have I noticed any correlation between doing well in these and success in academia? Yes and no. Definitely there's many successful mathematicians that have never done any of these competitions. And you hear people talk about all the time the fact that doing mathematics in the real world is much more a marathon than a sprint, whereas the Olympiad is a sprint. But let's go look at and so that's all true. You don't need to do Olympiad to be successful. Uh, let's see, list of. Yeah, so I mean, we've got but also, Peter Schultz's and Terry Tao and Perelman and Chow have all won Fields medal. Mirzakhani, so I don't want participants. I want gold. I want gold medalists. Oh well, whatever. I think you get the point, right? And there's no shortage of other. Okay, yeah. Here's a list. So Terry Tao, Venkatesh, maybe some of these other names are famous to other people, but Noam Elkies. That's a pretty famous name. Drinfeld. Yeah. So I mean, uh, and then other high scoring participants. Like if you just go look through these lists, you'll find a lot of famous people. So yeah, I don't know. There's maybe yeah. I don't know. I don't know what more to say, but is it the best thing to put? Yeah, I don't know if it's necessarily worth your time to put all your stock in doing well in the Olympiad. I think it can open opportunities if you get a really good Olympiad score, but yeah, if you're young, maybe why not go for it? Um, couldn't hurt to spend some time working on Olympiad stuff, especially if you enjoy it. But if you don't enjoy it, there's so much more else you could do. Yeah, there's a correlation, but not a causation. You're right, absolutely. Um, yeah, I mean, I'm sure there's people who did the Olympiad and I think if you did the Olympiad, you probably already were uh, quite good at mathematics and going to be successful. And I'm sure there's a lot of people on that list that didn't go on to be successful mathematicians. But I would venture that probably if you're doing well on the Olympiad, you're probably um, I would guess that you're more likely to be doing well in life in various other departments. Again, it's not because you do well in the Olympiad that you do well in life. I'm not saying that if you do well in the Olympiad, you'll do life. Rather, I think it's the other direction. If you have the kind of life, the stability at home, the financial stability, and the intellectual drive and prowess to do well at the Olympiad, then, well, you'll probably do well in life. That's my guess. That's my hypothesis. But I don't think anyone's tracked the data to see how Olympiad medalists have fared against uh, other people. Um, okay. So we also talked about last time. We have this isomorphism of stocks. So basically, we start at the stock at one, right? We start at the stock at one. What is it going to be? We're going to have some function. Well, up to scalar multiple, it's just the first root of x. So, or root, the first kind of square root of x. So let's see what happens there. So we know from this isomorphism that really we can just take the germ that is root x1 u, and where will that get sent through the localization map, the stock map? Yo Vihar. I don't know, or is it Vihar? I don't know if I said that correctly. If I was 14 to 17, what would I do apart from Olympiads to immerse myself in mathematics? You're of a similar age, holding off of university, proper courses until university. Um, Yeah, I mean, I would just start with the basics and go hard on the basics. Like, get yourself some. Um, I think that's maybe a good age to do Olympiad stuff. To be honest, you pick up lots of problem-solving tricks that'll be useful. Um, but I would start with the basics. And of course, your studies in school are priority number one. But I would maybe grab a basic book on like proofs slash discrete math, a basic book on calculus, and a basic book on linear algebra. And just slowly start working through those. Well, I don't know where you are, how advanced you are. If you already understand a bunch of pre-calculus stuff, then you could go on to calculus or something. But maybe you're at a point, if you're already working on Olympiad problems or something, maybe you're ready to start thinking about proofs. So if you're ready to start thinking about proofs, then yeah, a book on like discrete math, an introduction to like how to prove things, maybe Axler's linear algebra done right, to look at linear algebra from a very proof based perspective. But you also need to find something you like, right? So maybe you'll find that a book on like elementary number theory by like Underwood Dudley or something. Um, maybe you'll find that more agreeable. So there's a lot of directions you could go in. I mean, of course, yeah. In university one, you learn calculus and whatever, but that's maybe not so fun, in my opinion. I mean, I don't know. I taught myself some calculus in high school, and I loved it at the time. So actually, maybe, yeah, I don't know. That's what I would do. I mean, follow what you're interested in. Try and keep it structured. Try and make it structured, but follow what you're interested in, right? Do some exploring, find some subject of interest, and then yeah, yeah, dig in. So, um, on this computation now, so we're following around this loop, right? We go from our stock at 1, we lift it up to a section over u, and now we want to go back down to a stock at -1. Oh, you're currently working on Spivak. Nice. Well, then I think a great thing to do is, if you're enjoying Spivak, then I would just keep at it, and just trying to keep progress, keep trying to go as far as you go, but also just trying to really understand things, really make sure you do the exercises well, understand the solutions very well. And focus on building up a strong base. That would be my recommendation. Yeah. Hello, duck with a monocle. So we can go back down. We can go back down to the stock. Maybe I'll write it this way. We can go back down to the stock at -1, and again we can just take the open set u. But now I want to. I'm gonna want to take the isomorphism that takes me back up to sections over v. And so I'm going to want to rewrite this in terms of v, but now I need to write this as an equivalent section of u, but my theta is going to be off here, right? So hopefully you can see that what I need to multiply by is So I think this is true. So this should be theta 2 multiplied by e to the minus I pi, right? Well, wait. What do I need to multiply? I'm just gotta do some basic math here. So, right. I basically just need to. I need to rotate it. I need to. If I'm avoiding this line, I need to rotate it so I avoid the other line, which is, right. That should be e to the I pi. Well, which is the same as e to the minus I pi, but either way. So, right, yeah. So it should be like that. So we have to pick up this factor. Then, of course, we take the isomorphism over the sections of v, and that just gives us with this second square root times this factor. And then finally, we want to go back down and localize at the stalk again. The stalk at 1, which is going to be, so again, this will be v. The sort of obvious thing is to take it as such. Yes, that's I am alive. I am alive. Quality content. I am alive. Oh, now I'm confused because now I want to reconvert this to the first square root, but that makes me think that my e to the I pi will disappear. And I don't want that to happen because I already know what the answer to this should be. Oh, wait a second. I might have written something. Sorry, let me think about this for a second. So actually, we should have had... so the first square root is, say, ei like this. Right, if z is r, ei theta. So actually, yeah, did I want to multiply by ei pi? Yes, I think I did, because multiplying by ei pi makes this r e I theta plus 2 pi over 2. Oh, no, that seems weird. Okay, no. So I wanted pi over 2 because I think I just wanted to add pi to go halfway around the circle. So maybe I wanted pi over 2. Maybe that was my issue. Yeah, maybe that was my issue. Actually, and maybe I made a mistake somewhere in the translation of the stock. Am I sure? Am I sure that these two functions are the same if I shrink them? Surely they must be, right? Yeah, so this is the section over LV, and then this should be the socket L1. And then I'm still a little confused though, because I want to replace this with the first square root. And I thought that would shift this back. Oh, yes. Okay, perfect. Right. Um, right. It doesn't shift it back, but I need to multiply by e to the I pi over 2 again. That's what it is. So that becomes e to the I pi, which is minus 1, which is exactly what I wanted. Yes. Okay, great. So we took our loop gamma, and from it we obtained a map from L1 to L1. So, and I should say this is gamma 1, right? So this is our generator of our fundamental group. And how does it act? Well, basically, our representation of the group is entirely determined by what it does, by how the generator acts. And so, essentially, the generator acts by minus 1, we just found. Right? We checked it on our 1 basis element, and it had the effect of multiplying by e to the I pi, which is minus 1. So in other words, if we take what this means then is under this equivalence of categories between local systems and representations of the fundamental group, or, okay, sometimes it's written like this. I just wrote it like this because let me write it as representations. Then the square root local system exactly gets sent to the representation of the integers, which just sends an integer to minus 1 to that power. And that's it. And we're done. So I think that'll do it for today. But yeah. So now we've seen the connection between local systems and representations of the fundamental group. We also talked previously a little bit about D modules, right? We saw that basically, I wrote down some examples previously. Well, no, we haven't talked about D modules. Well, secretly we did, right? I talked about a quasi-coherent sheaf with a connection. We saw that this local system, as other local systems, can arise as the kernel of a connection on a quasi-coherent sheaf. And so next time, tomorrow, I guess, we'll maybe talk about the definition of D modules, and we'll talk about how to go between that and quasi-coherent sheaves with a certain kind of connection. Yeah. All right. See y'all, I don't know, when I see you. Go prove